Before we derive the elimination rate constant, you must have idea about two formula of integration and one rule of integration. The first formula is integration 1 upon x dx is equal to natural log of x. And as this integration which we are performing is indefinite integration, your answer should always be written along with one integration constant. Let us say it is C1 over here. The second formula, it is integration of dx or 1 dx is always equal to x plus integration constant, that is C2. See that in case of indefinite integration, your answer will be always associated with the integration constant. The numbering which I have given over here is just to differentiate C1 and C2 from one another. C1 is the integration constant of the first formula, C2 is the integration constant of the second formula. The rule which you have to remember over here is that you cannot integrate a constant. For example, suppose you are integrating a dx over here and this a is a constant, then you cannot integrate a. You have to take it outside the integration sign. So integration a dx will be always written as a integration dx. And if you solve it further, a cannot be integrated, so you are only going to perform integration of dx. And integration of dx, you all know that in second formula we have written the answer already. Integration dx is x. So answer of this integration will be a x plus, again we have to incorporate the integration constant, that will be C3 over here. Okay, so the first two formula and this rule is going to help you out to derive the elimination rate constant from our equation number 1. So first I will write down the equation number 1 over here. So our equation number 1, it was dx upon dt is equal to minus ke, that is elimination rate constant, into x. So firstly, before performing integration, we are going to take similar terms on one side. So what I will do, I will take the x term towards the side of dx. And when I do that, the x will come to the denominator towards left hand side. And I'm going to take this dt term towards right hand side. So when we perform the rearrangement over here, we will get the equation as given below. So your equation now will be 1 upon x dx is equal to minus ke into dt. Now we are going to integrate both sides of this equation. So if we perform the integration of both the sides, then your equation will look like this. Integration of 1 upon x dx is equal to minus ke integration of dt. See that this minus ke is a constant. You cannot integrate it as I have stated in the rule. So you are going to take it outside the integration sign. Now once you do that, we are going to use formula 1 and formula number 2, which we have seen in the previous section. So if we solve this integration, your answer will be integration of 1 upon x dx is nothing but it is natural log of x plus integration constant c1 is equal to, I will write minus ke as it is towards right hand side, and integration of dt is going to be t, because integration of dx is x, integration of dA will be a, integration of dt will be t. Okay, so t plus our integration constant c2. If we solve this entire equation, you will get natural log of x plus c1 is equal to minus ke. We are going to multiply the entire term present in the bracket with this minus ke, so minus ke t minus ke C2. This is what we are getting. Now, in this entire equation, you will see that this C1 is a constant and this Ke into C2 is also a constant because Ke is the elimination rate constant and C2 is the integration constant. So what I'm going to do, I'm going to take this C1 towards right hand side. So if I do that, the equation will become natural log of x is equal to minus Ke t minus Ke C2 minus C1 because here C1 was having positive sign. If we take it towards right hand side, it will become negative. Now, this entire term which you are observing over here, okay, this entire term is nothing but it is a constant only. So what I'm going to do, I'm going to club this thing. I'm going to club these two constants over here, and instead of writing these terms completely, I'm going to use only a single alphabet for all these constants, and that will be capital I. That is the integration constant, a complete total clubbed integration constant. That is what we can call it. So if this entire term, this KEC2 minus C1 is clubbed together, then we will get one constant that is capital I. So I can rewrite the equation as natural log of x is equal to minus KET. This minus sign which is there, that I'm going to keep as it is, minus, and this term that is KEC2 minus C1, that will be nothing but it will be integration constant I, which is the clubbed constant over here. Now see, if I consider that time is 0, okay, so let us say that at time 0, t is equal to 0, your x, that is the amount of drug in the body, it will be x0. That will be the initial concentration, means the concentration of drug when it was injected into the vein. That is x0. Means at time 0, the amount of drug present in your body will be x0. If that is the case, then this equation, let us call this equation as equation number 2 over here, because our equation 1 was the previous one which we had written. So if I put these values over here in equation number 2, then I can find out the value of this integration constant. So let us put these values in equation number 2. So instead of this t, I will put 0, and instead of this x, I will put x0. So by putting x is equal to x0 and time is equal to 0 in equation number 2, we will get equation as natural log of x0 is equal to minus ke. Now time is 0 over here, so it will be 0 minus I. So if you solve this thing, you will get natural log of x0 is equal to minus k into 0 will be 0 minus I. So from this, we will get the value of integration constant over here. So integration constant I, it will be equal to minus natural log of x0. So what we have done, 0 minus I will be minus I. So value of I will be minus sign will go towards other side. So it will go to logarithmic terms. So I will be equal to minus natural log of x0 over here. Okay. So this is your equation number 3. Now what we will do, we will put this equation number 3 in equation number 2. So put equation number 3 in equation number 2. And so what we are going to do, we are going to put the value of I which we have got in equation number 3 in the value of I which is present in equation number 2. Okay, so equation number 2 is over here. Here is the I, and instead of this I, we are going to write minus natural log of x0. So if we do that, your equation will become natural log of x is equal to minus ke t minus into bracket minus natural log of x0. So if you solve this equation further, minus into minus will be plus. So the same equation now can be written as natural log of x is equal to minus KET plus natural log of x0. Okay. Now see, our final aim is to determine the elimination rate constant, means only we have to finally determine this value. So what we will do, we will take this KET term towards left hand side and logarithmic terms towards right hand side. So if we rearrange the terms, then we will get, if we take this KET towards left hand side, so minus will become plus, so we will get KET, this minus sign will going to become positive when we take this entire term towards left hand side, is equal to, now you are going to take this natural log of x towards right hand side. If you do that, you will get natural log of x0. You are taking this natural log of x towards right hand side now. If you are doing that, it will become negative. So natural log of x. Now once you do that, what we have to do over here is that we have to write the logarithmic term in the form of a ratio. For example, if you know a general logarithmic formula, that is natural log of a upon b is nothing but natural log of a minus natural log of b. So if we revert this formula and apply it over here, then in that case, this entire term can be written as KET is equal to natural log of x0 upon x, right? So now the next step will be to convert natural logarithm into log to the base 10. And whenever we are converting natural log to the base 10, our formula which we are going to remember, it is that natural log of a is equal to 2.303 into log of a. Okay, so this is the basic formula which you have to remember. That is natural log of a will be equal to 2.303 into log of a. So if we use this formula over here, then we will get KET is equal to 2.303 log of x0 upon x. So finally, you can determine the elimination rate constant, and that will be KE is equal to 2.303 upon T into logarithm of x0 upon x. So this is the final equation using which we can determine the elimination rate constant. But besides that, instead of amount of drug present initially within the body and amount of drug present at time t within your body, which is yet to be eliminated, we have to substitute the amount of drug terms with the concentration terms over here. Now, if you want to substitute the amount of drug terms with the concentration terms, then you have to use one formula, and that formula will be X is equal to volume of distribution into concentration. Okay, so this is the general formula which we have seen in case of topic distribution. So the same formula we are using, that is amount of drug in the body, will be equal to volume of distribution of that drug into plasma concentration. What we are going to do over here is that we are going to substitute the x0 and x value over here with the concentration terms. So for x, it will be Vd into C. For x0, it will be Vd into C0. Right? So instead of x and x0, we are going to put value Vd into C and Vd into C0 over here. Now see, the volume of distribution is going to stay constant only over here. Right? As volume of distribution is going to stay constant, put these values, okay, substitute the value of x and x0, which we have written over here in this above equation. So if you do that, your equation will become Ke is equal to 2.303 upon T into log of Vd multiplied by C0 divided by Vd multiplied by C. So the VD will get cancelled over here, and so final equation will be, therefore elimination rate constant Ke is equal to 2.303 upon T into log of C0 upon C, where C0 is the initial plasma concentration at the time of injection and C is the concentration of the drug within the plasma at time T. Now let us see how to determine the elimination rate constant graphically. For that, first we will write down the final equation of elimination rate constant which we have got previously. And that equation is Ke is equal to 2.303 upon T into log of C0 upon C. Now we are going to rearrange this entire equation in such a way that the final equation should look like equation of line. For that, what we will do is that I will take this t term towards left hand side and also this 2.303 towards left hand side. So t will go towards numerator, 2.303 will come towards denominator. So if I rearrange the things, then I will get equation like Ke t upon 2.303 is equal to log of C0 upon C. Okay. Now, whatever this logarithmic term is there, I'm going to re-simplify it. Means we had reached to this logarithmic term from one equation, that is log of A upon B is equal to log of A minus log of B. Now, initially, this term was log of C0 minus log of C, and using that formula in reverse manner, we had come to this logarithmic term, that is log of C0 upon C. And again, we are going to revert it back. Means instead of writing log of C0 upon C, we are again going to rewrite it as log of C0 minus log of C. So the equation will become, therefore, Ke T upon 2.303 is equal to log of C0 minus log of C. Now, again, I'm going to rearrange the terms. I'm going to take this log C towards right hand side and this KET upon 2.303 towards left hand side. So if I rearrange the terms, means if I take this log of C towards left hand side and take this entire KET upon 2.303 towards left hand side and rearrange the things, then the equation will look somewhat like this. Log of C is equal to log of C0 minus KET upon 2.303. So now I can again write this equation in another form, and that form will be log of C is equal to log of C0 plus, in bracket I will write, minus KE upon 2.303 bracket complete into T. Now, if you look this equation looks like equation of line, where log C, it represents Y, log C0, it represents intercept C, minus Ke upon 2.303, it represents the slope, that is M, and time T, it represents X. So, using this equation, we can plot a graph, and from the slope of that graph, we can determine the elimination rate constant. So if you take log C on y-axis, time on x-axis, then you are going to get a declining straight line, and slope of that declining straight line is nothing but it is minus Ke upon 2.303. So once you determine the slope, multiply that slope with 2.303. Of course, your slope is going to be negative over here because the line is declining. As the line is declining, slope will be negative. Multiply that negative value of your slope with 2.303 so that finally you can reach to the value of elimination rate constant graphically.